So, chapter 1. Now that we kind of have an idea what we want to do, let's get into the nitty-gritty. So, section 1.2 is sort of approximating limits. And the definition of a limit. So we're going to define what this new creature is, this operation or this idea of taking a limit means. So let me start you with a sort of motivating example. So let f of x equal x cubed minus 8 over x minus 2. A, fill in the following table. B, use the table to guess which y value the function approaches as x approaches 2. Now, before I do anything or say anything else, let me just talk about this. So I gave you a function, x cubed minus 8 over x minus 2. First of all, right away, you should see that denominator and know I cannot plug in 2. Right? If I try to plug in 2, undefined, division by 0. Yeah, boo. Okay. So what I'm saying is, instead, let's make a little table to see what we think to see what the function could be defined as at x equals 2. Okay, what it gets close to. Now, if you have a graphing calculator, then you probably have a table function. But since I'm not letting you use graphing calculators, if I give you something like this on a quiz, you'll have to use your scientific calculator. But if you have a table like f of x, and I give you specific x values, none of these are equal to 2. Right, so you should be able to calculate your function at all of these. I'll show you one pretty quick way to do it. I have all the answers. Let me give them to you while I'm waiting for this to warm up. So how would you actually do this, though? If it were a test and it were you and your scientific calculator, what would you have to do to calculate f of 1.9?
Plug in the value for each x.
1.9 cubed minus 8 divided by 1.9 minus 2. Calculate. Figure out what that decimal is. 1.99 cubed minus 8, 1.99 minus 2. 1.999 cubed minus 8. Okay, so you'd have to plug in each of these to each of the x's. Here's what you get. 11.41, 11.9401, 11.994, 12.006, 12.0601. That's what I got. One quick way to get these values, at least if you have a phone or a computer around, you can go to the calculator that I gave you the link to in the syllabus. And you can put your function in, which is x cubed minus 8 divided by x minus 2. Minus 2.
X.
And then you can, instead of getting the graph, you can go up here. Oops, wrong. Oh yeah, there it is. Convert to table. And then it'll give you this table format. And you can put in whatever you want. All right, we wanted negative 1.9. Oh, positive 1.9. There we go. And we wanted positive 1.99. We wanted 1.9999. So you can get all your values pretty quickly.
Yeah.
So that's a handy little tool. If you're doing homework. On a test, you're going to have to use your scientific calculator. Okay, and I'll try to give you maybe a slightly less complicated function, but nonetheless. So what about B? So this is the table, but how can I use the table to guess which y value the function approaches? What does it look like your function's approaching? 12, right? Function approaches 12. Right, because as you get closer and closer to 2, right, x equals 2 is actually going to give you undefined. But as you get closer and closer from either side, you're zeroing in on 12. Right, 12.006, 11.994. This is zeroing in on 12. So even though the function's undefined there, it's approaching 12. And if you look at the graph, this is even more clear. So it's trying to plot the points that I have on there. So when x is 2, even though there's a denominator in my function, it doesn't matter, right? My function is still approaching the y value of 12. Now let me ask you this question. I have a denominator of x minus 2, which means that x equals 2, my function's undefined, but I do not have a vertical asymptote. Right? Clearly, from that function in my graph there's not a vertical asymptote. Why do you suppose that is? When the denominator is 0, you have a vertical asymptote if you do what first? Simplify. Right? If you reduce, then the denominator equals 0 is a vertical asymptote. What this is telling you, this graph, because it doesn't have a vertical asymptote, this actually reduces. This x minus 2 cancels. Right? You could factor out this difference of squares and cancel the x minus 2. Your function's still undefined there, but it doesn't have a vertical asymptote. It approaches one number. So this is the idea of a limit. Right? We would write, for this particular function, we would write lim, standing for limit, as x goes to 2, because we're letting our x values get closer and closer to 2, of our function equals 12. So this behavior right here can be summed up with this statement. The limit as x goes to 2 of this function equals 12. Another way you can write that, you can put as x goes to 2 with a little arrow, f of x goes to 12. These are equivalent. The point of this section is, one, being able to make these kind of calculations where you just plug in numbers nearby and get the limit and get the result, right? Find the y value you're approaching. But also study what, maybe when a limit doesn't exist, okay? Or other ways that we can find limits without approximating. So let me give you, actually not the formal definition, but a more technical definition of what a limit is. The formal definition of a limit is really very mathematical and you can't get your hands on it. Okay, but most books will give you a sort of watered down version. That's what I'm going to give you now. This is the thing we're going to be studying throughout this whole chapter. So if a function f of x, if the y value of a function f of x, becomes arbitrarily close to a single y value, let's call it L, as x approaches c, some number c, and you need to approach c from both sides, you need to become arbitrarily close as you approach c from both sides. Then the limit of f of x as x approaches c is L. Or, instead of saying the limit of f of x as x approaches c is L, that's equivalent to saying lim x arrow c, limit as x approaches c of f of x equals L. So this is kind of the mathematical notation for that last sentence. This guy here. This is how you write that in that. So I'm going to do I'll do however many examples I can do today, and then more of them next time I see you. Right? To get this idea. But let me make sure you kind of get the language here. If f of x becomes arbitrarily close to a single y value L, as x approaches some number c from both sides, then you can find this limit. So look at that in the context of what's going on here. What would my c be? 2, right? Because I'm focusing on what happens as x gets closer to 2. What would my L be? 12, right? Because that's my single y value that everything's approaching. From both sides, what's that mean? Yeah, if I go a little bit less than 2, I'm still getting close to 12. And if I go a little bit greater than 2, I'm still getting close to 12. For example, if I put in 2.001, and instead of getting out 12.006, I get out 20, the limit wouldn't be 12 because you're approaching two different things. Right? You'd be going to 20 or whatever on this side, and you'd be going to 12 on the other side. Right?
It's not negative.
No, it's not negative and it's just a little bit less than 2 and a little bit greater than 2. If this were 0 here, then it would be negative and positive. But if it's not 0, it won't be negative. So these y values you're getting out of this table have to approach the same number on both sides. And then the last thing, arbitrarily close. What do you think arbitrarily close means? Right, but what's almost mean? Ridiculously. Okay, ridiculously close. Good. So the way, mathematically, the way you define arbitrarily, this is one of the main reasons this definition is soft and squishy and not hardcore math. Okay, this is weedy. Okay? But what we mean by this is no matter how close you want me to get to 12, I will get there eventually. So for example, say I wanted to get within 0.0000001 of 12. Right? I wanted to get within 1/1,000,000th of 12. Then I can pick an x value close enough to 2 so that my y value is within 1/1,000,000th of 12. So, whatever sort of tolerance you want. Right? If I want to get within 1/1,000,000th of 12, I can do so by picking an x value close enough to 2. That's what this means. Let me leave it at that. Let me do some more examples. Some different examples. so I just put analyze each limit. And what I mean by that is find the limit if you can. Figure out what it is. If you can't, then tell me why you can't. Limit as x goes to 2 of x squared. So your biggest advantage right now for this problem, for these kind of limit problems, is either to make a table, which you really shouldn't have to do all the time, especially not for something like this. But that's one tool. Okay. The other tool you have is the graph. All right. So let's talk about graphically what this means. Okay. What does x squared look like? It's a parabola. Vertex at 0, 0, right? So here's x squared. X equals 2, right? So here's 2. So what this problem is saying is as x approaches 2, what y value does your graph approach? 4. Because there's actually a point there. Right? As x gets closer to 2 from either side, if you translate that to what it means on the graph, your y values are getting closer and closer to 4. So as x zeroes in on 2, your y values are going to zero in on 4. Does that make sense? So this limit equals 4. I picked x squared because, I don't know, it's my favorite, I guess, today. I've been using x squared a lot. But there's really nothing special about x squared. Right? There's something called continuity. That's what's actually special here. If your function doesn't have any breaks, and it doesn't have any holes, and it doesn't have anything weird going on, it's just a one piece, one curve in one piece. You can draw it without lifting your pencil. Then you'll always be able to plug in the number to find the limit. See, all we did was plug in 2 to get this limit.
Question. Is the limit answer always a whole number or it could be a decimal?
Could be this. Could be this. Yeah. So, for example, to sort of illustrate what I was just saying, what if I asked you for the limit as x goes to, I don't know, 5 of x cubed?
75?
Close. 125. How'd I get that? Just cube 5. Right. So if you have a function here that's a polynomial, okay, or something else that's easy that you can just plug into, that'll give you your limit. Why couldn't we do that on this example? Do you remember? Because f of x had a 2 in the denominator. Yeah, so x couldn't be 2, so we couldn't just plug it in. Okay? But if you have a nice function where you can just plug it in, that will give you the limit. All right, here's your snake. Here's 5. As you get closer to 5 on the x, the y's are going to get closer to 125. Right? Because you're approaching this point. Questions? Does that make sense? Yeah.
I started to do it, and I made a x squared minus 4 over x minus 2, and now I'm like confused. Is it that 2 cubed is 8? Is that just arbitrary? You just pick that on like the first one? Or you did x cubed minus 8 over x minus 2?
Oh, this function's arbitrary, yeah.
So the fact that like 2 cubed wouldn't be is 8 just happened?
Well, yes and no. I purposely picked these two polynomials because they cancel very easily.
Okay.
Like if I would have picked x cubed minus 9 over x minus 2, it doesn't It doesn't cancel as nicely. Okay. But that has nothing, that has really very little to do with this here because we have no denominators here.
Okay.
See, that's the main difference. This is a function with a denominator, these aren't.
Yeah, I just started to write x squared minus 4 over x minus 2, so it's like the same as what you did.
Well, but x squared minus 4 over x minus 2 is going to cancel to x plus 2. So then you'd have to take the limit as x goes to 0. No, that's way too hard. No. I kind of see what you're doing, but you're making it too complicated.
Okay.
Absolutely. Absolutely. If you don't have a problem, at that number, right, if your function's continuous at that number, it doesn't jump, then you can just plug the number in. That's kind of the model. But let me look at an example like what you're talking about. So what about, for part C here, what if I ask you the limit as x goes to 3 of x squared minus 9 over x minus 3?
But that one it's x minus 3 times x plus 3.
Right, so one way to do this again would be to make this table, but I kind of want to get away from this, okay? Because this is just guessing, okay? Another way to analyze this is to say, well, can I simplify this at all?
Yes.
Yeah. So this rational function here can be rewritten as x minus 3x plus 3 over x minus 3. So if you're trying to calculate what happens as x goes to 3 for this guy, you can simplify a little by getting rid of your x minus 3 factors. So this will be the same. Now, as soon as you write this, as soon as you see this denominator, you know that x cannot equal 3. Limit doesn't care about x equals 3, though. Limit doesn't give a poop about x equals 3. It cares about what happens as you approach 3. Okay? So what I'm saying here is I can look at a graph of this function now. What does the graph of this function look like? It's a line.
It's a line.
Through 1, 2, 3 on the y-axis, up 1 over 1. So something like this. But where does this x not equal to 3 come into play?
When it reaches a y value of 6.
Right, so this 3 is going to give you a hole, right? X not equal to 3 means you have a hole at x equals 3 on your graph. You have a hole right here. But limit doesn't care about a hole, right? Limit wants to know what's happening as you get closer to 3. Well, on the graph, as I get closer to 3, I'm getting closer to that hole. And on the y-axis, as I get closer to the hole, I'm getting closer to what y value? 6. How do you get that? Now you can just plug the 3 in. Limit doesn't care. Limit doesn't care about this x not equal to 3. You plug 3 in and you get 6.
So how come that would be? Oh, never mind.
Right, so this function here is actually just a line with a hole in it. And the limit as you go to x equals 3 is still going to be, it's going to be whatever y value the hole took out. By, what if I asked you limit as x goes to 1 of x squared minus 9 over x minus 3?
Simplify close.
Do you have to simplify it here? Actually, no, you don't. Because 1 is not a problem. This function is perfectly well defined at 1. It has a hole at x equals 3, but at 1 there's no problem. And if I can actually just plug in 1 here and get negative 8 over negative 2.
4.
I could do it this way too and just plug in 1 at the end. 1 plus 3 is 4. Get the same thing. Right? But because there's no problem at 1, I can do my limit by just plugging in. If there were a problem, then you'd have to try to simplify first or turn to your table. I'll give you one more. Oh, we don't have time for those. We'll save those for next time. Those are fun. We'll do these. We'll do these instead.
Don't we need a table on this one?
Maybe.
Or the graph?
Maybe. Or the graph. Or the graph. Certainly a graph would be nice. Table will work too. So let me toss up the graph real quick because we talked about those I think last time a little bit. 1 over x versus 1 over x squared. 1 over x squared goes to positive infinity at the asymptote. Whereas 1 over x goes to positive infinity on one side and negative infinity on the other.
Oh yeah, it's the second this supposed to with side.
So if we're thinking about what happens as x approaches 0,
Versus infinity.
so as x approaches 0,
I don't know.
my graph is going up and up and up, so you want to say your y value is approaching infinity. Unfortunately, the definition does not allow for infinite y values. The way the definition of a limit works, in order for the limit to exist, it has to approach a finite number. So for now, at this point in time, we are going to say this limit does not exist. It does not exist. Later in section, I don't know, 1.5 or something like that, we do talk about what an infinite limit is. And we will be able to say this equals infinity. But for now, according to the only definition we know, you have to approach a finite number to exist, and this does not approach a finite number because as x goes to 0, y gets bigger and bigger and bigger and bigger. But there is a fundamental difference between this and this. What do you think the answer is here?
Negative and less infinity.
0.
Does not exist again. Right? As x gets closer to 0, on one side your y values are going up. On the other side your y values are going down. But they're not coming to a consensus. So this one does not exist. But kind of for a different reason. Okay? Kind of. This one I would say does not exist. The biggest problem with this guy is that you're going in different directions. On one side you're going down, and on the other side you're going up. It's really bad. This one doesn't exist because you're not approaching a finite number. Okay, but they are going in the same direction, so that's a little better. All right, I'll pick up here. I have a couple more examples. Let's say we're probably about halfway through 1.2. So I'll finish that off on Wednesday after our quiz.